curves. The next question is, and going around the ellipse, how does it go? Does it go faster when it's near the sun, slower when it's further from the sun, and so on? We take away the other focus, we have the sun then and the planet going around. And Kepler found the answer to this too. He found this, that if you put the position of the planet down at two times separated by some definite time, let's say 3 weeks, and then at another place in the orbit, put the positions of the planets again separated by 3 weeks, and draw lines from the sun to the planet, technically called radius vectors. But anyway, lines from the sun to the planet, then the area that's enclosed in the orbit of the planet and the two lines that are separated by the planet's position 3 weeks apart is the same no matter what part of the orbit the thing is on. So that it has to go faster when it's closer in order to get the same area as it goes slower when it's further away, and in this precise manner. Some several years later, he found the third rule, and that had not to do with the exactly motion of a single planet around the sun, but related the various planets to each other. And it said that the times that it took the planet to go all the way around was related to the size of the orbit, and that the times went as the square root of the cube of the size of the orbit, and for the size of the orbit is the diameter all the way across the biggest distance on the ellipse. So he has these three laws, which are summarized by saying it's an ellipse, and that equal areas are swept in equal times, and that the time to go around varies as a 3/2 power of the size, the square root of the cube of the size. So there's three laws of Kepler, which is a very complete description of the motion of the planets around the sun. The next question was, what makes them go around? Well, how can we understand this in more detail? Or is there anything else to say? In the meantime, Galileo was investigating the laws of motion. Incidentally, at the time of Kepler, the problem of what drove the planets around the sun was answered by some people by saying that there were angels behind here beating their wings and pushing the planet along around orbit. As we'll see, that answer is not very far from the truth. The only difference is that the angels sit in a different direction and their wings go in a different direction. But the point that the angels sit in a different direction is the one that I must now come to. Galileo, in studying the laws of motion and doing a number of experiments to see how balls roll down inclined planes and pendulums swung and so on, discovered an idealization, a great principle called the principle of inertia, which is this, that if a thing has nothing acting on it, if an object has nothing acting on it and is going along at a certain velocity in a straight line, it will go at the same velocity at exactly the same straight line forever. Unbelievable though that may sound to anybody who has tried to make a ball roll forever, the idealization is correct, and that if there were no influences acting, such as the friction on the floor and so on, the thing would go at a uniform speed forever. The next point was made by Newton, who discussed the next question, which is when it doesn't go in a straight line, then what? And he answered this way, that a force is needed to change the velocity in any manner. First, for instance, if you're pushing it in a direction that it moves, it will speed up. If you find that it changes direction, then the force must have been sideways. And that the force can be measured by the product of two effects. First, how much does the velocity change in a small interval of time? How fast is the velocity changing? How much is it accelerating in this direction, or how much is the velocity changing when it changes direction? That's called the acceleration. And when that's multiplied by a coefficient called the mass of an object, or its inertia coefficient, then that together is a force. One can measure for instance, if one has a stone on the end of a string and swings it in a circle over his head, then one can measure, when one finds one has to pull, the reason is that the speed of the velocity, the speed is not changing as it goes around the circle, but it's changing its direction, so there must be perpetually an in-pulling force, and this is proportional to the mass, so that if we were to take